apologize right up front. I have a bit of a cold, and so if my voice, don't be surprised if my voice fades to a whisper by the end of the 75 minutes. What I'd like to do today is give you a little bit of an overview of the device requirements for RF integrated circuits of the type that Professor Abadi mentioned during the previous session. And one of the things that I think came out of that was a very crisp explanation of some of the key figures of merit or key important aspects of an integrated circuit technology for RFIC applications, and in particular the issue of dynamic range and DC power consumption are probably the two most key aspects of a technology for RFIC applications. And so based on that, that's sort of what we'll focus on in our discussion this morning. And so what I'd like to do first of all is give you a little bit of an overview of the impact of device scaling on RF performance. And the last last decade or two has seen an absolutely astonishing level of device scaling for integrated circuit technology, and I don't need to review that for this audience in particular. But what I'd like to do next is then focus in particular on the device aspects that result from this scaling and how they impact particular circuit building blocks for an RFIC. And I'll start by giving an overview of the device impact on low noise amplifiers, which are in one sense one of the key building blocks for any RFIC, because in a sense they set the minimum sensitivity as was defined in some senses by Shannon's limit earlier in the talks. What I'll do next is sort of march down the chain of the various blocks that are required for a typical RFIC implementation. I'll next talk about mixers, both CMOS and bipolar, and how they're affected by device issues. And then I'll talk about voltage-controlled oscillators. Voltage-controlled oscillators are the key circuit elements that take a frequency at one level and up converted or down converted to another level. And then finally, I'll talk about the very important area of power amplifiers. Power amplifiers are kind of a unique category in and of themselves. And in many ways, they defy our best attempts to integrate them along with the rest of the building blocks on the circuit. And so we'll talk a little bit about how the particular challenges of a power amplifier make integration very hard, and in particular, what sort of unique device requirements are required of these devices. So as we've seen before, the communication environment is characterized by many different aspects, one of which is, as we saw a little bit earlier, the shared medium. And the shared medium very often means that the channel that the device has to work in, the RFIC in this particular case, the channel is essentially hostile, and so it has to accommodate many of the things that Professor Abadi mentioned earlier, the fact that we have interferers in the channel passband that may overwhelm, in some cases, the desired signal. So this particular challenge of the shared medium is one of the unique aspects of almost any communication system. And this is kind of a generic block diagram of a typical monolithic RF transceiver as of the type that you might encounter if you opened up your cell phone and looked inside of it. And it has a variety of both active and passive devices. Despite our best efforts, the external filters, usually surface acoustic wave filters, but also duplexer filters, are still a very common feature of an implementation like this. And so one of the key aspects of the research within the research community is trying to eliminate these passive elements. But this shows both the receiver and the transmitter sections of a typical sort of generic receiver, which we talked about earlier. And this handset architecture that I showed you earlier can be fairly dramatically simplified, as Professor Abadi mentioned, and in particular for something like a Bluetooth radio transceiver, which is a very simple kind of cable replacement application. The goal, in fact, is to build the entire thing on a single integrated circuit die, both the RF portions as well as the analog baseband, and in fact even the digital. And we'll hear a little bit more about that later today. So in some cases, that rather complex block diagram can be simplified to its bare minimum to just create a low-cost link. And in the handset, on the receiver side, things can get very complicated in terms of the choice of the appropriate technologies. And today, this is just a kind of a classic example of a third-generation wideband CDMA receiver which is an emerging third-generation standard, certainly not widely deployed yet, but it will be in the coming years. And the results that have been published to date with this particular class of applications typically uses a gallium arsenide HBT or even a PHEM for the power amplifier. And so this would be sort of on the transmitter side. That very last interface to the antenna is often built in a 3.5 technology. And then on the receiver side, most reported implementations to date have been in a bi-CMOS technology, most commonly silicon germanium based. And then further down the chain, this would become an all CMOS implementation, often married with a digital baseband approach. So the performance requirements, like for a third-generation wireless standard, are much more severe than for a simpler standard like Bluetooth. Now, one of the things that, the third most important thing for wireless standards after dynamic range and power dissipation is cost. And the cost trends for wireless handsets, in fact, for wireless devices of all kinds, have followed the standard trend of all electronic systems over the last several years, whether it's a personal computer, an 802.11 wireless LAN, a cellular telephone, a GPS receiver. They all have a per unit cost that drops dramatically for a given performance as a function of time. So at the same time that we're integrating all of these features onto a common integrated circuit, we have to be reducing the cost constantly in order to meet market goals. Now, in fact, a fully integrated version is not always the best choice in a radio frequency environment. And in fact, very often what we find in the radio frequency environments is that the cost and performance of discrete passive devices like filters and off-chip inductors is really improving dramatically at the same time. And there are many legion examples in the RFIC industry where a discrete implementation of a certain function has actually displaced a fully integrated version because, as it turns out, the discrete implementation is cheaper. So we have to be very careful in an integrated circuit environment that we don't build a very large and expensive chip that will eventually be, that could in fact be supplanted by something that's not so well integrated. So this chart sort of summarizes the technology requirements for a variety of different high-frequency communications applications. And I've also thrown in here some wireless and some wireline and fiber optic-based systems as well to kind of show the complete picture or the complete spectrum of communication integrated circuit applications, what the environment looks like. Now in the wireless field, the key requirements, as I mentioned before, are really very low DC power and at the same time very low cost. Now these wireless systems are, of course, they also have very high dynamic range requirements, as Professor Abadi mentioned before. So how do you simultaneously achieve very high dynamic range, very low DC power, and very low cost? Well, one of the ways is through the use of the most appropriate technology and design expertise that's available to you. And so what I'd like to talk about during this lecture is what are the most appropriate technologies and how does the choice of technology affect the performance both in dynamic range and DC power of the resulting circuit. Now, so I'd like to start at the very, very beginning by sort of doing a materials-based technology comparison. And there are many different possible technologies or semiconductor materials that you could choose from in order to implement a communication integrated circuit. And in fact, almost every possible semiconductor technology has a little niche within the communications universe. Silicon is, of course, Silicon is, of course, the most common technology of all, and we'll spend most of our time on that today. But gallium arsenide also has some very fundamental advantages compared to silicon, and gallium arsenide retains a kind of a strong niche within the power amplifier field for reasons that I'll talk about a little bit later. From a technology perspective, sort of the key issues are the electron mobility, breakdown voltage or breakdown field, and then the maximum charge density that you can get in a given conducting channel. Gallium nitride is a device technology that I won't spend much time on today, but it has some real potential advantages for base station power amplifiers in the coming years, and it's a very active area of research within the device research community. And the fundamental advantage with gallium nitride is not so much the mobility, which is rather modest, but the breakdown field is about an order of magnitude better than even gallium arsenide. So if they can make this technology work quite well, very, very high power linear amplifiers are a distinct possibility. Now, when we talk about dynamic range, the key things are sort of the difference between the upper and the lower range of the allowable signals. And the lower limit is set by, essentially by KTB, which is, and B is the bandwidth in this case. So that essentially sets the minimum noise energy level in any given system. And that's why as bandwidths increase, dynamic ranges tend to drop for any kind of communication system. And then at the upper limit, there's essentially a Johnson limit, which is a breakdown voltage speed trade-off in its most simple form. And so the Johnson's limit basically sets an upper limit on the device range. And so as we go to higher frequencies, what we see inevitably for any given semiconductor technology, silicon, gallium arsenide, whatever, is that the dynamic range tends to compress. It compresses on the lower side because the noise floor is rising, and it compresses on the top side because the device requires a higher speed, and as a result will have a lower breakdown voltage. So what we typically see with all of these technologies is that the dynamic range is compressed at the higher bandwidths. But there's a fundamental limit or a fundamental improvement that these 3.5 technologies in particular provide to us, because although sort of KTB stays constant, somewhat independent of technology, we can push the voltage to higher and higher levels with the alternative technologies. Now, in most cases, the ability to go to a higher and higher voltage level is not particularly useful, because the digital logic actually tends to limit the voltage in a kind of a commercial consumer application. But as it turns out, it's very important for power amplifiers, and that's why gallium arsenide remains important. So I'd like to focus on silicon technology first, for the obvious reason that it's by far the most widely used technology, and in fact for everything except the power amplifier, it's the most commonly used technology in a communication receiver, at least for RFIC applications. And today the silicon germanium HBT is probably the most common bipolar device. Certainly most new fabs that are implementing bipolar devices are implementing them using an HBT process. And this is a cross-section of a typical device showing the emitter and base and collector, and then this is a very nice photograph from IBM showing the cross-section of the device. Now, as we'll see in just a second, the performance of many of the key elements in an RFIC, it might be the low-noise amplifier or the mixer or the VCO, one of the key performance elements actually is the FT of the device. Certainly, it directly affects noise figure. And the FT of a bipolar device is given by this expression right here, which accounts for the base and collector transit times, as well as some of the other parasitic capacitances around the device, the junction capacitance and the collector base capacitance. And the FT is, of course, the frequency where the current gain goes to 1 in the device, but perhaps a more important figure of merit is the Fmax of the device, which is the frequency where the power gain goes to unity. And for an HBT, these frequencies are typically roughly the same. For a modern device, it might be in the range of 100 gigahertz. And this is a plot of a variety of reported measured results of both the FT and the Fmax of a silicon germanium HBT as a function of base thickness. And what we see is that there's, not surprisingly, a very close correlation between the base thickness and the FT, with the FTs rising fairly dramatically in recent years. And I believe at this conference there's a 300 gigahertz FT device, so that must have about a -3 nanometer base width. But but nevertheless, these devices continue to scale at a fairly impressive rate. Now, what we see is that the FT can rise fairly dramatically, but the Fmax is a little bit more of a challenge, because very often as you scale, especially the base width, the extrinsic base resistance begins to grow, and the collector-based time constant is linearly proportional to that resistance. So the FT goes up, but the tau goes up as well, and the ratio doesn't improve dramatically. And you sort of see that on reported Fmax results, where there's not a very strong correlation with base width, base thickness. And so one of the key challenges, this is well known within the community, one of the key challenges for bipolar scaling is keeping the ratio of Fmax to Ft fairly constant as you improve the Ft of the device. Now, how do silicon devices compare to gallium arsenide devices or 3.5 devices? And once again, the intrinsic advantages of a compound semiconductor technology manifest themselves at a higher Ft for a given base thickness. And this is shown by this data here from a variety of different laboratories. And as before, there's a very clear trend of Ft with base thickness, and the same trend is exhibited with the 3.5 devices, but there's an offset of about 2 to 1 perhaps. For a given base width, the performance is better. Now, as I said before, and as we'll see as we get into the presentation a little bit, this sort of intrinsic advantage doesn't buy you a whole lot, because actually, as Professor Abadi said earlier, the existing technologies are good enough for almost any application. The one exception is with power amplifiers, where we often operate them right to the very, very limits of their breakdown voltage capability. And so here we can, and every little bit of extra Ft that you get at that limit has a big impact on performance. So, and since power amplifiers loom so large in power budgets of modern transceivers, this becomes a major issue. Now, with MOSFETs, once again, the scaling is fairly straightforward, and the expressions for Ft and Fmax are quite similar to those of a bipolar device, where the 1 over the Ft is given by the product of the transconductance and the gate source capacitance, plus some additional effects due to parasitic source and drain resistances. And once again, the gate resistance begins to have a major impact on the Fmax of the device. The gate resistance, gate drain capacitance time constant, if not properly handled in device scaling, can have a major impact on the Fmax of the device. So one of the challenges that confronts us as we scale the MOSFETs is how do we keep the performance from an RF perspective, which includes the Fmax, at an acceptable level as the gate length is scaled. Now, these are some plots that were reported at IEDM several years ago of Ft as a function of drain current for a variety of different technologies. This is a 1/4 micron device, and these are 0.18 micron devices. And you can see some interesting features of this graph. First of all, it's fairly clear that there's a very modest dependence on drain source voltage. The electrons get a little bit faster at the higher drain source voltage, but it's not a dramatic effect. And there's a huge difference, or a significant difference perhaps, between a 1/4 micron device and a 0.18 micron device. And finally, for applications in the 1 to 5 gigahertz range, which is where 99% of RFICs are today, really almost either of these technologies is adequate. So from a kind of a mass commercial marketplace perspective, both CMOS and bipolar technologies are now at the place where they can address pretty much all the system issues. So there's a dynamic range issue with, or breakdown voltage issue with MOSFETs that I'll return to in a second. Now, if you look at the reported Ft of an Fmax of MOSFETs as a function of gate length, you notice something slightly interesting. A MOSFET, a sort of traditional MOSFET, should exhibit a very high Fmax, because under normal scaling, under a larger gate length regime, the gate resistance is really quite low. And so early MOSFETs, in the sort of 0.5 micron range, had a very respectable Fmax over Ft ratio. And what that sort of meant is that their power gains were quite high, even if their current gains were rather low. But as the gates have begun to scale down to shorter and shorter dimensions, the ratio of Fmax to Ft has converged, and now they're rather like bipolar devices. The ratio is very close to unity. And part of this is, of course, due to the fact that the gate cross-sectional area is shrinking fairly dramatically as the gate length shrinks. And of course, that raises the gate resistance as well. As we continue to scale the gate length of MOSFETs down to sub-10th micron levels, metal gates may be required, or some other kind of metallization scheme may be required in order to keep the gate resistance from limiting the performance of the RF devices. Now, there's one class of MOSFETs which is different from traditional MOS devices, which is very, very commonly used in the RF business, but it's rather quiet, and it's a very unique custom kind of a device, and that's what's known as an LDMOS device. LDMOS devices are probably used in 95% of all base stations worldwide because they're able to produce extremely high powers in a very, very low cost manner. So LDMOS devices are RF devices that have a real unique use within the RF field, but they're very, very different from traditional CMOS devices. And in fact, they tend to be built on kind of fully depreciated, crummy lithography lines, and they tend to be as a result, very, very inexpensive. And but the LDMOS device has some interesting lessons from an RF perspective that should be examined. And one of which is that they typically have a drain which is offset from the source by a fairly significant region. And this offset is what allows the breakdown voltage of the devices to be very good. A typical sort of 1 micron or 0.8 micron LDMOS device might have a 30 to 50 volt breakdown voltage. Another interesting aspect of the LDMOS device is this P+ sinker. They're typically fabricated on a very heavily doped P+ substrate, and there's a very, very deep P+ implant that connects to the substrate. And then the source is connected to the sinker, so there's an incredibly low inductance path from the source down to the ground, and the ground is connected to the back of the substrate. So these devices are in some ways really tailored for RF power applications, and you can do that with MOS devices, but the process variations that are required to do that are often very incompatible with digital technology. And these, as I said, have been used for base stations, and there have been some attempts to use them in the CDMA handset market, but without too much success because of the voltage requirements. Now, so that's a kind of a brief overview of transistor scaling and some transistor performance issues. And another absolutely crucial element of a successful RFIC technology is the performance of the passive devices. And we'll be hearing a lot more about passive device performance later on this afternoon. But one of the key elements of an improved passive technology is the very simple expedient of being able to build a very thick top-level metallization. And the top level of metallization is usually what is employed to build high-quality factor inductors on an integrated circuit. And so the thicker you can make that metal, the lower the series resistance, and therefore the higher the quality factor. So there's been a real sea change in recent years, say from 5 or 10 years ago. We've been able to, once again, I'm hitting the wrong button, I apologize. We've been able to increase the thickness of the top layer of metal fairly dramatically. And this has resulted in a very dramatic increase in the quality factor of the inductors, in this case from Q of about 7 to well over 10. And as we'll see in a little bit, that improvement in quality factor has an absolutely direct result in improved VCO performance in particular. Now, one of the ways that we can accomplish this improvement in performance is, as I said, to go to a thicker last level metal. This is a Backend stack from IBM. And a thicker final layer of metal just lowers the series resistance. And as we evolve to copper metallization, you can even strap 2 of these metals together and have a copper layer here, and then put that in parallel with this thick layer of aluminum, and reduce the series resistance even further. So, and I'm sure that there are more and more of these types of schemes being developed in process labs throughout the world. One of the things that you notice with the improvements in metallization is that there is an absolutely direct improvement in inductor quality factor that has resulted from this over the years. And this is a plot of the peak quality factor of an inductor as a function of inductance for a variety of different integrated circuit options. And basically, there are several sort of trends here that you can observe. One is that as you go to thicker layers of metallization, the quality factor gets better for a given amount of inductance. The second thing that you can notice is that going to sort of exotic substrates like silicon on sapphire or gallium arsenide gives you some improvements as well, because the losses in the substrate are essentially eliminated through an insulating substrate. One of the things that we see in silicon is that there has been an emphasis on increasing the substrate resistivity, using maybe float zone silicon or something else. And that might even boost us up a little bit further in the coming years as the resistivity of some of these substrates grows higher and higher. And once again, that's a very active area of research. The second thing that metallization allows us to do is improve the inductor quality factor through going to copper rather than aluminum. And this is a plot of the improvement in peak quality factor, once again, for different inductances simply by going from aluminum metallization to copper. And once again, we pick up almost a factor of 2 in inductor quality factor by going to a copper-based metallization. So this is very, very key for future highly integrated, high-performance radio frequency integrated circuits. Now, there are other things that you can do as well, kind of at the substrate level, and I mentioned one thing that you can do, which is going to a very high resistivity substrate. But there are other tricks as well at the substrate level to improve RFIC performance. Certainly, the use of deep trench isolation, which has had a big impact on the improvement in bipolar device performance, can also be used to raise the effective resistivity of substrates underneath, say, inductors or capacitors. So one of the things that this does is have a modest impact on quality factor for inductors, once again by lowering substrate losses. The other thing that deep trenches allow you to do is provide very effective isolation between different areas of the circuit. For example, you might have a digital circuit in one section of the chip and a very sensitive analog section in another portion of the chip. And through a combination of deep trenches and substrate contacts, these two areas can be effectively isolated from each other. And we'll hear also some more about that in talks this afternoon as well. Now, so that sort of completes the device, what you might call the device physics aspect of this problem. We've looked at transistor scaling. We've looked at passive component scaling and some of the issues. And what I'd like to do now is turn my attention to some kind of circuit-oriented aspects of the performance of an RFIC, and how does all of that device scaling stuff that we've talked about, how does that impact the circuit performance? And the first thing is the noise figure of the receiver. The noise figure of the receiver essentially determines the minimum signal that you can receive for a given wireless receiver, and it has a huge impact on the kind of the economics of this business. For instance, a 3 dB increase in noise figure essentially cuts in half the number of users that can kind of roam within a cell site. So that's why in a wireless standard, a noise figure is such an absolutely important figure of merit for any kind of receiver. And for a MOSFET, the noise figure is essentially given by this expression right here. And you can see that there's a weak dependence on the gate series resistance, which gets into the scaling that I talked about a little bit earlier, how as we go to shorter and shorter gate lengths, the series gate resistance can become a significant issue. And then the intrinsic transconductance thermal resistance of the channel is given by this expression here. And once again, the FT of the device has a significant impact on the minimum noise figure. So a higher FT is better, but up to a certain point, the improvement is small because of the gate resistance limiting factor. Now, the bipolar device, not surprisingly, has a very similar kind of set of trade-offs for noise figure, except that in the bipolar device case, the base resistance is very significant. And with modern scaled bipolar devices, actually the extrinsic base resistance is in many ways the key limiting factor. And then once again, there's a noise factor which essentially depends on the transconductance of the device and the FT, very much like the MOSFET. And then there's a final term which actually depends on the current gain, or beta, of the transistor. And this is the one area where bipolar devices have a slightly worse kind of intrinsic noise figure than MOSFETs. This shot noise in the base tends to slightly raise the noise figure in some cases. Now, this is a plot of the comparative noise figure performance as a function of frequency for a, pardon me, for a variety of different technologies. And this is actually comparing gallium arsenide with silicon germanium bipolar devices, and then I'll compare MOSFETs with silicon germanium bipolar devices in just a moment. But you can really see that, like, the silicon germanium HBT has a noise figure, and this is a sort of a 50 gigahertz device, has a noise figure which is really very comparable to about half micron gallium arsenide MOSFET. And if you go down to sort of the 2 gigahertz frequency range, which is where the bulk of the applications are, the minimum noise figure is certainly less than a dB, perhaps 0.8, 0.7 dB. And you really have to go to a very exotic quarter micron gallium arsenide pHEMT to see a dramatic improvement in noise figure. Now, once again, the difference of a few tenths of a dB in a wireless system is not that significant because there are many other factors that tend to raise the noise figure of the system rather dramatically. So for applications below about 5 gigahertz, silicon germanium HBT device, as an example, is very adequate for most communications applications. Certainly, there's no compelling reason to go to gallium arsenide. And in comparison to MOS devices of comparable FTs, the MOS devices tend to exhibit a slightly lower noise figure of a few tenths of a dB, maybe 2 or 3 tenths of a dB. And this is essentially due to the fact that I believe the gate resistance of the MOSFET is intrinsically lower than the base resistance of a bipolar device for a given kind of FT and geometry. And second, the base shot noise current also adds to the noise figure as well. Now, the minimum noise figure is lower for a MOS device, but this lower minimum is typically achieved at a slightly higher source impedance and at a slightly higher current. So in practice, if you sort of compare the performances of LNAs based in two technologies, they'll have roughly comparable noise figures despite the fact that the MOS device has a slightly better intrinsic noise figure. Now, the second absolutely crucial thing for low noise amplifiers is the linearity of the device. And Professor Abadi gave a very nice overview of linearity considerations in receivers in the last talk, so I won't sort of belabor this. But essentially what we want to do with the receiver is maximize the distance between where the desired signal, this is on the receive side now, where the desired signal sort of pokes up above the noise floor and can be seen with a decent signal-to-noise ratio, and where this large jammer or a large undesired signal also pokes up above the noise floor at the same frequency. So the distance between these 2 points is known as the spur-free dynamic range, and this is really the thing that we're trying to maximize. We're trying to maximize the spur-free dynamic range for a given DC current for these technologies. So this is the thing that is the most crucial, and we've just looked at the first aspect of this, which is now noise figure. So let's spend a little bit of time on linearity. Now, at very high frequencies, the linearity of any device, bipolar device or MOSFET, is really fundamentally limited, as it turns out, by the variation of FT with DC current. And what you would like to see, this is under some rather specialized conditions, which essentially boil down to the fact that the device has to be operating at a relatively high frequency. And what you essentially want to do is you want to minimize the variation of FT with DC current. So in order to build a very low noise receiver or a very low noise mixer, what you'd like to do is optimize the device so that its FT varies as little as possible as a function of DC current. And in fact, the results, the expressions for the output intercept, third order output intercept point and second order output intercept point reduce to some things that are very simple, as it turns out. For instance, the second order output intercept point is essentially the FT divided by the derivative of FT with respect to current. So once again, if it's very flat, if the FT is very flat, the output intercept point will be very high. And then similarly, if for the third order intercept point, it's a little bit more complicated, but under the limiting case of at the peak of the FT curve, the output intercept point is given by essentially the ratio of the FT of the device to the second derivative. So what you would like to do in order to build a very, very linear device, this is now not a low noise device, it's a very linear device, is make the FT versus IC curve as flat as possible. And this is, there's a variety of experimental confirmation of this. This is a plot of the output intercept point as a function of current for a gallium arsenide HBT, but this theory works for really all devices. And it shows the output intercept point for two different collector emitter voltages. This is at 2 and at 5 volts. And you can see that the theory agrees quite well with the experiment, even including these sort of odd-looking peaks. And this is one of the things that you notice with most bipolar devices in particular, that the linearity is a very complicated function of the DC current. And there are some DC current levels where the linearity mechanisms actually cancel out. and so resulting in a very, very high output intercept point. And you can also see that the 2-volt peak in the FT corresponds roughly to the peak in the output intercept point, and the 5-volt peak in FT corresponds roughly here as well. So this is a good rule of thumb that you can use for device scaling purposes when you're trying to optimize for linearity. And in fact, you can do a Volterra analysis on the device and predict its intermodulation level as a function of DC current. And the Volterra analysis actually sort of predicts many of the features that this kind of more fundamental theory will predict. And in fact, the key factors for reducing third-order intermodulation is to basically, there are several things that you can do. One is you can just increase the DC current, and that works up to a certain limit quite well. And then you can also decrease the base transit time and decrease the dependence of the base collector capacitance on either voltage or current at high currents. And so we'll be talking a little bit more about this issue of the base collector capacitance in just a second, because it has a big impact on the overall linearity of the circuit. So basically, IM3 is minimized by minimizing the, if you go back a couple of slides, one of the things that we saw was the linearity of the device is maximized if the FT at the peak is as flat as possible. And in order to do that, we want to minimize all voltage-dependent capacitances within the device that are not transit time related. And so that means essentially minimizing the base emitter junction capacitance within the transistor. And of course, an HBT in general is an extremely good device from that perspective, because the emitter can be relatively lightly doped compared to the base. The second thing is that going to a scaled emitter design improves the FT of the device as well, and the scaling of the FT as we go to shorter dimensions will improve the linearity as well. And then we want to, as much as possible, minimize collector doping and parasitic resistance, being careful not to have the Kirk effect become a significant feature. Once the Kirk effect takes over with the bipolar device and the FT begins to crash, the linearity is pretty much destroyed. And so what this means from a very simple perspective is that there's a kind of a sweet spot for every given generation of bipolar scaling from a linearity perspective. And basically what you want to do to minimize the Kirk effect is make sure that the collector resistivity is less than a certain amount, so that at high current densities the device doesn't enter the Kirk effect region. You want to have as high a breakdown voltage and as high a gain as possible. So that means that you really, in fact, you want a very high collector resistivity. And then finally, you want a low depletion voltage, because you want the collector to punch through under relatively low voltages, so that the device is quite linear over a large regime of voltages. So there's kind of a sweet spot right in the middle of these three conflicting regions where the optimum device design is achieved for a given, and of course this region changes depending on the base transit time and the typical generation of the technology. So these are the things that when we're scaling bipolar transistors, especially for linearity applications, high linearity applications, that we want to keep in mind. Now, this is a plot that Professor Leo de Vriend at TU Delft did several years ago that I think illustrates some of these issues in a very nice way. And these are results of a two-dimensional numerical simulation of a bipolar transistor and its linearity as a function of collector-emitter voltage and collector current. And you can see several features of the linearity of the device as you move throughout this region of bias. And essentially there's a sweet spot for all of these devices, which tends to be at sort of moderate currents and high voltages, where the IP3 of the device, or the amplifier, is maximized. At very low currents, you're limited essentially by exponential distortion in the base emitter junction, and the linearity is rather poor. And at high currents and low voltages, you tend to be dominated by CBC distortion. And then at extremely high currents, you have the onset of quasi-saturation, and that becomes an issue as well. So there's a kind of a sweet spot for almost all of these devices at high currents and, moderate currents and high voltages where the linearity is maximized. Now, this particular simulation was done in a 50 ohm environment and was done for sort of cable TV applications where linearity is absolutely crucial. But I think the simulations, nevertheless, are equally valid for lower voltage, lower power applications like wireless communications. Now, one of the things that you notice is that this is a fairly narrow region of optimum performance. If you go too low in current, the linearity starts to suffer, and if you go too high, it suffers as well. So you have to be very careful with these devices in order to choose what you might call the sweet spot in order to get the best performance. And then another way of cutting this curve is to change the collector thickness and the collector doping, and once again, there's a kind of an optimum sweet spot, which is essentially analogous to the chart that I showed you on the previous page. Now, we can extend this issue a little bit further and look at comparisons between technologies again. And once again, this is some work that Professor De Vries published at the BCTM this year, where he looked at the effect of the choice of materials, silicon versus gallium arsenide, on the linearity of the transistor. And in particular, in this case, we're looking at the behavior of the base collector capacitance between the two technologies. And one of the things that you see with gallium arsenide, which is very interesting, is that the base collector capacitance actually drops and then rises again as you increase the bias. And this is due to the fact that the negative differential mobility in gallium arsenide it increases the transit time so much that the base collector capacitance actually goes back up again a little bit at the higher voltage levels. By comparison, silicon devices have a rather benign base collector capacitance behavior. So the question is, what is the effect of this sort of differing base collector capacitance variation on the linearity of the device? And if you recall from that several slides back, the behavior of the FT is very crucial for linearity determinations. And the base collector capacitance is one of the key determinants of the FT. So this is a, pardon me. This is a plot of the comparison. Once again, these are numerical simulations of silicon germanium devices and gallium arsenide devices as a function of collector voltage and current. And what you can see is that the peak of the linearity is not as large for silicon germanium devices as it is for gallium arsenide devices. It's still quite respectable, but not quite as large. But also the region over which the linearity peaks is much narrower for the silicon devices than for the gallium arsenide devices. And once again, if you sort of go to engineering lore, one of the things that you always hear is that gallium arsenide HBTs are incredibly linear devices, and that's why they are by far the most dominant power amplifier technology for CDMA applications. And I suspect a lot of it has to do with this very, very large region of high linearity compared to the somewhat smaller region for a silicon germanium device. So basically, from a linearity perspective, and remember we started off talking about noise and then we switched to linearity. From a linearity perspective, the gallium arsenide HBT has the best potential for linearity, and that's why it's, from a commercial perspective, the most dominant device. But of course, there are cost issues. So if we examine silicon germanium devices, they're potentially more linear than silicon. But there are some things that you can do to improve the linearity of these devices. You need to use a very steep doping profile in the collector region. You want to optimize the current gain to be very linear. So you want to avoid any hint of an early effect. And to as large a degree as possible, you want to lower the base resistance by boosting the base doping. And once again, this will flatten out the FT curve. All of these measures essentially flatten out the FT curve over a wide range of different regimes of current operation. Now, what I'd like to do next is spend a little time talking about how we can improve the linearity of the low noise amplifier by exploiting some of these nonlinear characteristics of the transistor. I mean, is there anything we can do sort of at the circuit level to improve the linearity of the sort of the intrinsic linearity of the device? And for low noise amplifiers, this is very tough because any little circuit thing that you do to a low noise amplifier usually adds some noise to the resulting circuit. And that added noise, of course, hurts the sensitivity of the receiver. So the standard linear design procedures for low noise amplifiers are very mature. It's a very mature and well-established field. And But the question of how do we impedance match a device, or how do we design an amplifier to get the best linearity, this is still an evolving field. And engineering lore, once again, states that the linearity is roughly optimized when the source impedance is large. This is the passive network that we would apply to the device right here. And when the output is essentially conjugately matched so that we get the best gain out of the circuit. And then the question is, what can we do? Is there anything else that we can do to the device at the circuit level to improve the linearity? And then that raises the question, what about the source and load impedance at the harmonics? And this is a plot of a typical common emitter low noise amplifier with impedance, kind of generalized impedances both at the both at the base and the emitter. And what we can do is we can look at this circuit as a feedback circuit. And if we analyze the circuit using a power series approximation for the bipolar device, and assuming kind of a general frequency-dependent feedback, it turns out that there's this rather long and complicated expression for the third-order nonlinearity. If you can think back to a polynomial approximation to the nonlinear response, this would be the third-order coefficient, and this would be the first-order coefficient. First-order coefficient is kind of the linear gain, and the third-order coefficient is what determines all the bad nonlinearity that we're trying to minimize. Now, this final expression, although it's rather complicated, it suggests a kind of an interesting thing. It suggests that if we could somehow magically choose the feedback f, we could, at least in theory, cancel the A3 term with the second thing. So if we choose the feedback properly, if we choose this numerator properly, we can effectively cancel out third-order intermodulation distortion. And this can have a huge impact on the spur-free dynamic range of the receiver, which, remember, is the difference between the input intercept point and the noise floor of the receiver. So the interesting thing about this resulting expression is that the feedback, this cancellation depends on the feedback not at the desired frequency, which is at omega 0, but at the sum and the difference frequencies. So you can imagine that if we have a 2 gigahertz signal, and we have intermodulation between the 2 gigahertz signal and a 2.1 gigahertz signal, the sum frequency would be at 4.1 gigahertz, and the difference would be at 100 megahertz. Now, neither of those frequencies are in the band of interest, so we have almost complete freedom to do whatever we want here. I say almost complete freedom, I'll clarify that in just a second, but we have quite a bit of freedom to play around with these feedback factors in order to try to minimize the intermodulation distortion. So if it were possible to do this, we could set G3 to 0. And if only it were so simple, but there are some techniques to get close. Now, one of the things that we can do is if we set the feedback at the difference frequency, the feedback factor equal to this expression right here, then we can, in fact, cancel out those two terms. Now, you might ask yourself, well, what is this A1 term here? And the A1 term in a bipolar device is essentially just the transconductance of the device. It's just the GM of the transistor. And the wonderful thing about bipolar transistors is that the GM is extremely well known. It's sort of determined by device physics. It's the DC drain current divided by the VT, the thermal voltage. So in a modern RFIC or any kind of modern bipolar process, the A1 term can be very, very precisely set at manufacture, and therefore it's actually possible to imagine that you could build a feedback network that would satisfy this equation in a very precise manner, within a few % accuracy. Now you might ask yourself, how does this work? Well, basically there are two essentially competing mechanisms that generate third-order distortion in these devices. One is the sort of intrinsic third-order nonlinearity, the A3 term in the power series expansion. And then the other is the second-order nonlinearity at the output, which through feedback is fed back to the input, and then that input mixes with that feedback signal mixes with the desired signal again through a second-order nonlinearity, and the result, 2 + 1 = 3, is a third-order nonlinearity. So what we try to do is we try to control the second-order term. We sort of use jujitsu on it. We try to use the second-order term to precisely come in and cancel the third-order term. And if the device characteristics are sufficiently well known, this is in fact possible. And in fact, it's been employed with great success recently in bipolar transistor amplifiers, which I'll show you in just a second. Now, as it turns out, this technique doesn't work so well in gallium arsenide technology, like with MESFETs or PHEMs, and it's also somewhat less effective with CMOS devices. And this is an example from Dr. Steve Moss, where he basically varied the source and load impedance at the second harmonic for a gallium arsenide PHEM device, and he only saw about a 1 dB change in linearity. And so this previous approach that I mentioned to you before works best for devices that have a strong, well-characterized nonlinearity, like a bipolar device. I mean, FETs, whether they're MOSFETs or gallium arsenide PHEMs, they're intrinsically highly linear to begin with, so the technique is not so effective, nor does it need to be so effective. So this is one example of where this technique has been used in a very promising way recently. This is some work from the MTT symposium of several years ago, where a simple low-noise amplifier, bipolar low-noise amplifier, was examined. And in this case, the source impedance at DC is plotted on the x-axis, and the source impedance at 2 ohmega is plotted on the y-axis. And the thing that I want you to sort of take from this is that there's a huge change in input intercept point as a function of the terminating impedances. And these terminating impedances are not at the desired frequency of interest. They're at twice the frequency or down at DC. So they have no impact whatsoever on the gain or the noise figure. All they do is just improve the linearity. If you do it right, the linearity just gets better and better and better, and nothing else changes. No more DC power is really required. So it can be very, very substantial with a discrete BJT, which was this case, but it's also been profitably used for integrated versions. And this was the result from Fong in August of 2000, where this was a monolithic bipolar low-noise amplifier. And there's a trap here at 2 ohmega, which essentially terminates the device at the second harmonic. And then by increasing the RF feed-in capacitor here, he was able to improve the input intercept point from -7 dBm to 1.25 dBm. So it's about an 8.5 dB improvement in input intercept point. And once again, there's no change in DC current. There's no change in noise figure or gain. So this is one of the really nice features of bipolar circuits, is that we have this extra tool in our kit. Now, what I'd like to talk about next is our device considerations for voltage-controlled oscillators. So we've talked about low-noise amplifiers. And low-noise amplifiers are really, in some sense, the key performance limiting stage of a typical wireless receiver. If the noise figure and the linearity are not adequate to meet the performance targets, there's nothing you can do afterwards to get the performance back. You're stuck with the degradation that you've encountered. So that's why we've spent most of our time talking about low-noise amplifiers. But then after that, voltage-controlled oscillators then become very, very important, because they have a variety of issues of a reciprocal mixing, where the presence of a large jammer nearby a small desired signal can be mixed down with the phase noise of a voltage-controlled oscillator and ruin the performance of the receiver. In addition, the voltage-controlled oscillator often determines the residual phase error in the demodulator. So the performance of the voltage-controlled oscillator is probably the next most important issue for an RFIC. And this is a very simple schematic of the device, the voltage-controlled oscillator, and essentially it's a resonant circuit with inductor and capacitor, and then it's presented to a cross-coupled pair of transistors that are biased at a constant DC current. And this is a bipolar version, but MOS versions are essentially identical. And the cross-coupled pair presents a negative impedance to the resonator, which is what makes sustained oscillation possible, because there's a positive resistance, residual resistance within the resonator itself. And then we change the frequency, we tune from channel 1 to channel 2 by changing the capacitance of the resonator, and we'll hear more about variable capacitor designs later today. So as with low-noise amplifiers, the major issue with a voltage-controlled oscillator is the noise. And the major noise sources in the VCO are the losses in the resonator, the resistance in the inductors in particular, the amplifier noise, the noise in these transistors down here, and then whatever noise is in the tail current source at the bottom. So these are the key device considerations that set the noise floor of the voltage-controlled oscillator. Now, the way we characterize voltage-controlled oscillator noise is through something called phase noise. And phase noise is essentially the single sideband noise power at a certain offset from the carrier frequency. If you look in the frequency domain, you'd expect the voltage-controlled oscillator to be essentially a delta function at the frequency of interest. But in fact, there's some residual spreading due to noise sources within the circuit. And if you amplitude limit the VCO so that all that's left is residual variations in the phase of the oscillator, then that's the power in those residual variations is known as phase noise. And due to amplitude limiting nature of VCOs, most of the noise is phase noise in these circuits rather than amplitude noise. So in the crudest sense, what we do with the VCO is we measure the ratio of the peak power at the desired frequency to the power in a 1 Hertz bandwidth at some offset from the desired frequency, and that's the phase noise of the circuit. And there are a variety of specs for phase noise in every wireless standard. Now, if we sort of look at that VCO from the previous page and we add all of the different noise sources, and once again, this is a sort of a bipolar-oriented circuit, but many of the same considerations apply in MOS. The principal noise sources are here, and if we look at the phase noise performance as a function of current, what we see is that the phase noise just gets better and better and better until it kind of limits. And the reason that the phase noise gets better and better is because as you turn up the current, the voltage across the inductor, across the resonator, is growing. And of course, since the phase noise is the ratio of the power in the desired oscillation to the noise power in the sidebands, as you raise the desired signal, the ratio is going to improve. And at least with bipolar devices, you reach a certain point and then it gets very bad again. And what happens is that the bipolar devices begin to reach saturation. And bipolar devices get very unhappy when they go into the saturation region and they store charge and the conductance increases dramatically. And the tank Q falls apart and the phase noise rises. So with bipolar devices, in fact with all oscillators really, there's a trade-off between power dissipation and phase noise. And so depending on the phase noise requirements of the system and depending on the current requirements, you need to determine the optimum spot to be on this curve. Now as it turns out, there's a fairly simple and yet pretty accurate expression for the phase noise in a VCO as a function of frequency and a function of most of the physical parameters, and it's known as Leeson's equation, and it was derived many, many years ago. And it highlights some of the key things that you see in all oscillators, fully integrated or otherwise. And I think that some of the key issues are that the phase noise is inversely proportional to the amplitude of the oscillation, which gets into the current dependence, and it's also inversely proportional to the quality factor of the resonator, which is a ratio of the energy stored in the resonant circuit to the energy dissipated in the resonant circuit per cycle. So we want to have a very high Q factor, however we could achieve that. And then there's this one last factor here, which is the so-called F factor. And F is somewhat related to the noise figure of the amplifier. Clearly, if you build a VCO with a good low noise device, a low noise amplifier would have a good noise figure, and a VCO would also have a very low value of F2. And in fact, the value of F that you get is pretty similar in some ways to the value of F that you get for noise as well. It depends on base resistance and on current and a variety of other things. One of the things that's very important for VCOs is the contribution due to the tail noise current. If you recall, there's a DC current source at the very bottom of the circuit that sets the DC current, and the noise power spectral density of it can upconvert to the output as well. And in some cases, this can really ruin the noise of the overall circuit. Now, there's been some very nice work done by Professor Abadi's group at UCLA on getting rid of that tail noise current source through harmonic tuning techniques. And basically, the idea here is that the noise at the second harmonic of the desired frequency upconverts directly to phase noise at the output. So you want to kill that as much as you can. And that can be harmlessly shunted to ground through the use of an inductor here and a capacitor here. And the noise current generated by this device looks up and it sees an inductor, and it looks to the right and sees a capacitor, and it all goes to ground. And the very simple explanation for what's going on, but the performance improvement is quite dramatic. There's with no filter and without it, and with the filter, there's maybe an 8 to 10 dB improvement in phase noise. So what that sort of does is it sort of allows you to build a VCO, a non-chip VCO, whose fundamental performance limit is limited by the quality factor of the tank circuit and the noise factor of the transistors itself, which ultimately what we're trying to do with these circuits is get to the point where we're limited by fundamental physical processes and not by extraneous biasing issues. So high resonator quality factor is the most important consideration for VCO phase noise. That basically means all the things I talked about earlier, very thick metallization, copper is better than aluminum. The upconversion of the tail current noise source can be minimized through appropriate filtering at the common mode node. And upconversion of varactor nonlinearities is a major concern at lower frequencies and higher amplitudes. As the amplitude begins to swing, the varactor diode that we use for changing the frequency has some nonlinearities. And the nonlinearities of that diode can actually upconvert into the desired band of interest. And MOSFET VCOs exhibit a little bit improved phase noise compared to bipolar devices, in large part because when the swing is very, very large, there's, the gate-drain junction doesn't forward bias in the same way that it does with a bipolar device, so that their saturation characteristics are improved. So actually the best monolithic VCOs reported today are usually in a MOSFET technology. And I'd like to very briefly now talk about MOSFET mixers. MOSFET mixers exhibit outstanding linearity. The best mixers from a linearity perspective are MOSFET mixers and passive MOSFET mixers. And, but they typically require a very, very high local oscillator power. You can go out and buy discrete, MOSFET mixers which have just astonishingly good linearity, but they require, several watts of power to drive them efficiently. And active MOSFET mixers require less local oscillator power, but they do exhibit these 1/f noise limitations that we talked about previously. So if linearity is the most key consideration, then a MOSFET approach is usually the way to go, but it requires a lot of supporting circuitry, which dissipates a lot of power in order to improve the performance. Now, a bipolar mixer, by contrast, rarely works well in the passive mode. And so the more common approach is a classic so-called doubly balanced Gilbert mixer, which is very widely used. And the Gilbert mixer, by comparison to a FET mixer, exhibits rather poor linearity, and the sort of ratio of linearity to DC power historically has not been very good. As Professor Abadi mentioned earlier, it's absolutely crucial to keep the size of these devices very small to get the best possible linearity and noise figure out of the circuit. And so this topology is very commonly used, and there's, from a circuit perspective, the route to improve performance is the same route that I mentioned for the low noise amplifier before. Using harmonic termination techniques, we can improve the performance of the bottom portion of this mixer without increasing the DC power or hurting the noise figure. And that's an area of some active research by a variety of groups. Now, I'd like to conclude with a discussion of power amplifiers. And as I mentioned, power amplifiers are kind of unique in the galaxy of RF circuits and devices from a requirements perspective. And the reason that they're unique is that they have to operate over their entire range of currents and voltages on an ongoing basis. There's absolutely no room to back off in any perspective in a power amplifier. You're always trying to operate the device. As Professor Abadi mentioned earlier, you want to operate the device right at its edge in order to get the best performance. In a typical CDMA power amplifier today, probably 97% of the DC power that's used by the battery that's drawn from the battery by the power amplifier just heats up the phone. Only 3% of that power goes out of the phone into the antenna. So most of the time when we're talking on the phone, all of that power, instead of going to the base station, is just warming up your hand while you're talking. So you want to operate these devices as high in efficiency as you possibly can. Even going from 3% efficiency to 6% efficiency is a huge breakthrough in many of these technologies. So the power amplifier is sort of unique from that perspective. The level of integration is less important than getting that extra little bit of efficiency. And the problem is not only the fact that they're that they break down, but their performance also tends to saturate or limit, as we saw earlier. And one kind of extreme way of looking at this limiting behavior is through a constellation diagram, and we saw some of these in the earlier chart. But typically, if you look at in the plane, the quadrature plane and the in-phase plane, the signal describes a rather bizarre trajectory. This is an 8qPSK waveform here. And if you basically take that nice, I say nice, but in reality, I mean, but it doesn't look very nice, but in fact it is very nice. If you take that nice trajectory and you squish it down by running it through an amplifier which essentially limits or clips at a certain level, you get the shape that looks like this. And the resulting the resulting spectrum exhibits what's known as spectral regrowth. It tends to rise up. Now, the problem with spectral regrowth, there are two things. One, of course, is that the constellation the accuracy of the constellation is destroyed. And the other thing is that there might be someone who's transmitting right here, and they're going to be very unhappy if you transmit in their channel with this junk. So the saturation characteristics of power amplifiers are absolutely crucial. You want to essentially like something to be linear out to infinity, and of course that's not possible. Now, from a device perspective, there are many, many different aspects of device design that impact power amplifier performance, and this sort of shows how each of the different characteristics of the device tend to impact the amplifier performance. And you can see why power amplifiers have their own unique subculture, because the trade-offs are highly complex and interdisciplinary. And in fact, this set of trade-offs is quite different from that typically used to scale a digital CMOS technology, which is why power amplifiers have tended to have their own, their own technology niches. One of the things that power amplifiers require is an extremely high-quality passive device technology supporting them, because although we tend to work in a 50 ohm environment in the world, the power amplifier likes to see a much smaller impedance, just a few ohms typically. And this requires a very high quality inductor capacitor network at the output. And actually, very typically, this high quality inductor capacitor network is realized off chip, because even though the inductors have gotten very, very good on an IC process, they're still not good enough to realize the performance that's required in a typical PA application. Now, in order to basically build a power amplifier with very good efficiency, you need as high a breakdown voltage as you can get. Even running off of 3 volts, the power amplifier might, under some conditions, encounter a 10 or a 12 volt surge. And I won't go into the sort of circuit-oriented reasons for that, but the higher the breakdown voltage that you can achieve, the better, even as we scale digital voltages. Now, this is one area where bipolar devices have a real advantage, I think. If you sort of plot the maximum VDS that is allowed for reliability considerations as a function of FT, it's typically below the BVCEO or BVCBO of a bipolar device. And remember that the BVCEO is the breakdown voltage when the base emitter junction is open circuited, and the BVCBO is the breakdown voltage when the collector base junction is short circuited. And there's this well-known relationship between the two. And so the question that perpetually plagues power amplifier designers in the bipolar world is which figure of merit is most important? Is it the BVCEO or the CBO? And it turns out that, not surprisingly, the breakdown voltage is dependent on the impedance that you present to the device at the base. And I won't go through the mathematics here. You could maybe do that afterwards. But the key factors for bipolar devices is that the relationship between the collector emitter voltage, breakdown voltage, and the collector base breakdown voltage, as expected, depends on beta, but it also depends on the base resistance of the device. So the base resistance includes, in this formulation, not only the sort of intrinsic resistance of the base, but whatever resistance that you put to the device. And so having a very high base resistance can really cause some problems with these devices, which is one reason that gallium arsenide HBTs typically have a relatively good breakdown voltage. They have an extremely low intrinsic base resistance. So the particular issue with bipolar devices is that they can be operated through an appropriate choice of base impedance up to almost BVCBO. And that can be, even for a 50 gigahertz device, that can be well over 10 volts. So these devices are in fact potentially very promising, even at the 50 gigahertz range, for very high power amplifiers through an appropriate choice of source impedances. Now, the absolutely best device for wireless applications is, for the power amplifier, is a gallium arsenide p-HEMT. They have the best linearity, the best efficiency, but they have been limited in their wider application due to the inevitable problems of cost in a 3.5 technology. One example of this is that the typical power amplifier is turned off periodically during operation in a handset, and unfortunately, p-HEMTs or MOSFETs in general, they don't turn off completely when the gate is brought to ground. So an extra device, typically a PMOS device, has to be added in series to really turn it off. And then that creates additional cost and complexity in the design of the power amplifier. Bipolar devices, by contrast, are sort of limited by thermal collapse. This is one of the biggest issues with these devices. And thermal collapse is a problem where, when the emitters are closely spaced together, thermal feedback tends to cause one device to hog all of the current, and eventually that device takes all the current and collapses. Now, this can be, there are circuit fixes to this problem. It's a well-known problem for many years. It can be improved through the use of a cascode device, which limits the positive feedback action on the bottom device, or through so-called emitter or base ballasting, where resistance is intentionally added to the device to essentially lower the positive feedback of the thermal junction. There have been some good results with silicon germanium power amplifiers, and these devices do not have the same breakdown voltage as a gallium arsenide device. They tend to be lower voltage for a given f sub t, but nevertheless, they do have some promising applications. Typical power added efficiencies, peak power added efficiencies for WCDMA applications are in the 33% range. And the biggest issue with the silicon germanium devices is their ability to withstand these large voltage excursions which happen during a transient upset. Someone grabs the antenna and the antenna impedance changes dramatically. So careful biasing and circuit design approaches allow the designers to achieve very good reliability, even despite the fact that the breakdown voltage is rather low. And then finally, the use of harmonic termination effects can improve power amplifiers as well, especially if there's a significant amount of nonlinear capacitance at the output of the device. And in particular, in a MOSFET, the drain to bulk and drain to source capacitance can have a limiting impact on linearity. It's, in some cases, not the major factor, but it can be perhaps a secondary factor. And so simply in the same manner that we used with the voltage-controlled oscillator and the low noise amplifier, appropriate harmonic termination technique can improve the performance of a power amplifier. And this is an example from the MTT of several years ago, where a second harmonic trap, both at 2 omega and DC, at the output of a power amplifier, this medium power amplifier in this case, had a very significant impact on the third order intermodulation levels at the output of the device. So under certain circumstances, these harmonic termination techniques can really improve the performance of devices that have limitations on linearity at the output. So I'd like to conclude by saying that fabrication and technology choices can really have a major impact on the performance of RFICs. It's a very, very significant area. Technology is key to achieving good performance. And modern CMOS technology can really address all RFIC requirements below 5 gigahertz, but you need a full suite of really good passive devices. You need good capacitors, good inductors, in addition to the outstanding active devices. Digital CMOS process all by itself is probably not cost effective except in the most low performance types of circuits. Silicon germanium by CMOS technology probably will exhibit the best performance, but then that has to be traded off against the higher cost that would be associated with the use of a bipolar technology. And then finally, for power amplifiers, that appears to be a rather secure niche where 3.5 technology, gallium arsenide HBTs in particular, still have a significant performance advantage and probably will for the foreseeable future. And then I'd like to just acknowledge all of these people who have guided me a lot in some of these issues. So thank you again. Thank you. I have 7 seconds.